Your local council, some of the world's leading scientists, even Sir David Attenborough have all said we're in a climate emergency. But what does that mean? And how is today different from yesterday or a year ago when parts of our area were in drought, when we had big bushfires and extreme weather? What can we learn from where our planet, our environment has been by looking back? Can we actually get a sense of what happens next? Silvia Frisia is with the School of Environmental and Life Science at the University of Newcastle. She looks at this very thing. Good morning.
Good morning.
So great to have you here with us this morning. Do you feel from the work that you do that we are in a climate emergency?
That's a very difficult question. Okay, from the work I do, I can tell you that we are actually in a very strange period because it didn't happen in the last 2.7 million years, which is a period called the Quaternary. And just to put it simple, is the period when humans actually, started.
Yeah.
I mean, we started as a real species, as human and stuff like that. The Quaternary, so this last 2.7 million years, is a period of time characterized by glaciation. So we know that we have glaciation and periods when we had no ice or deglaciation. And the most characteristic property of this period is that the carbon dioxide in the atmosphere was about 280 parts per million in the interglacial when there was no ice. When there was ice was all the way down to 180. Today we are at 400. So we have to go back in history before the time when humans actually sort of colonized and conquered the planet. And that's why I think you are correct. And people perceived this as a climate emergency because it really didn't happen before 2.7 million years ago. So do you want to ask me what happened before 2.7 million?
Yes, let's go there. That's exactly where I was going next. You read my mind. What did we see before 2.7 million years ago?
Yes, a fantastic story. It's called, forgive my, my scientific or these scientific terms, but it's called PETM, the Paleocene-Eocene Thermal Maximum.
Let's go with PETMA.
Right, PETMA. And, this occurred about 55.5 million years ago. So that's a very long time ago. But it's quite interesting because all the research point that there was a simple, massive, and this is the nice word, subdecadal burst of carbon released into the atmosphere, meaning that it's very similar to what's happening today.
Interesting.
And then it was followed by a slow release of carbon, so it continued for about maybe 20,000 years. And the recovery of Earth, I mean, this is natural. So the recovery of Earth after this massive natural catastrophic event took about 150,000 years. So this probably relieved to something like as much light carbon, okay, let me explain. Carbon is an atom and has some isotopes, meaning that the atom could be heavier or lighter. When it is lighter, we know that it is related to organic matter. So more or less, it's like burning fossil fuel. So we know that this massive relief of light carbon was due to the release of some storage that was probably methane. So here it is, a big burst which is natural, but it's, how can I say, it's sort of mimicking what's happening today.
Yeah.
And so what did it create? It created a massive acidification of the ocean, which means with dissolution of calcium carbonate, and we all know that, for example, coral reef consists of calcium carbonate, and it increased massively the carbon dioxide concentration in the atmosphere. But if we continue like the way we are probably going to reach the same. So what was the cause? Could have been a big earthquake or a big volcanic eruption, or some meteorite hitting the wrong spot. We weren't around at that time, so we don't know what might have happened, but the temperature rose 5 to 8 degrees higher, but it was already high because 55.5 million years ago, the temperature was already warmer than today. So imagine if we do the same thing.
How do we know this? Because what is left on the Earth today that shows us what was going on 55.5 million years ago?
Okay, again, I'm using a word. It's called climate archives. So it's geological or biological archives. And for example, everyone knows, I think, about ice cores, but ice cores don't go back 55.5 million. They go back 800,000, 900,000. I personally work on something called stalagmites, which are calcium carbonate, or limestone people, deposit formed in caves, and they can go back millions and millions and millions of years. And, marine sediments, lake sediments, and also they go back a million of years. And these are called archives because they contain chemical and physical properties. I mean, I was talking about isotopes. So they contain, for example, the isotope of carbon. If they consist of calcium carbonate, in the carbonate there is carbon. So by measuring and dating, because we can date with various techniques, by measuring the amount of light carbon, we can actually mark where we have some of this catastrophic event. And this 55.5 is actually a huge spike, sudden spike of light carbon, which is called carbon-12.
Given we're seeing this sort of mimicking, what can we predict about what happens next with our climate?
Okay. I look at past climates. So in reality, what I look most is periods when humans were not around as they are today.
Yeah.
So we know how the Earth atmosphere, the temperature, the sea level rose. So we can understand about that. But 55.5 million years ago, for example, the configuration of the continents was different. So it is difficult to predict exactly. But what we can do is we can give this data to people who make model, and then they could play with those. And already, they could say, yeah, okay, given the configuration today of the continents, and given, for example, that today we still have Antarctica there, but we can predict, for example, that Antarctica will melt. But we know in my studies of what happened 120,000 years ago, which is already, it's nearer than 55.5 thousand. We already know that part of Antarctica melted, because we look at various archives, and the sea level was higher than today. So we know that we are getting there. So we could already say, listen, probably a lot of cities that are now at sea level will be inundated.
Where does the human element come into the work that you do? How do those two sit alongside each other?
Well, again, I look in the past. So what I look at is how human reacted when there was already a civilization, because it's very difficult to know how humans reacted when they were in the Paleolithic or the Neolithic.
They weren't good at writing journals.
But, for example, it is true that starting already 10,000 years ago, the archives see a strong impact of humans. And the more you go into a structured society, the more it becomes difficult for humans actually to cope with, for example, a long drought. And we know that there were very long droughts. The problem is that if you have a structured society as we do have now, we cannot move very much, because wherever we move, there are humans. And, right. And we cannot, for example, look for other places where, like to plant our crops. Because in reality, I think that the biggest problem is that humans are everywhere.
It's been really interesting to find out about the work that you do as part of this conversation. I think it's a part of the climate conversation that I certainly hadn't heard. So I really appreciate your time this morning. Thank you.
Thank you. Thank you for having me.
You're more than welcome. That's Professor Silvia Frisia. She's with the School of Environmental and Life Science at the University of Newcastle.